This is example 4-4, air escaping from a tank. So as you can see from our picture, we have this tank right here, and it has an opening, and there's air escaping out of this tank, which obviously means that the pressure inside the tank has to be higher than outside, so that it flows out. Right? And we're now asked for a very specific point in time to find out what the volume rate of what the density change is at that specific time, and we're given the pressure and the temperature inside of the tank, which allows us to figure out what the density is, and we're also given what the outflow rate is at that specific time, right? At 0.05 cubic meters per second. We're also asked if the flow is going to be steady or unsteady. So maybe we start with there, right? Steady flow meant that I'm not changing the velocity over time. Of course, if I have air that's pressurized in this tank and is then flowing out, then the pressure inside of this tank is going to drop, which means the driving force is going to get smaller and smaller, which means my velocity, my outlet velocity, is going to go down over time, which means we have unsteady flow. All right, so now that we have that out of the way, let's start by drawing a almost said free body diagram, but this is not statics. So we're going to draw our control volume. Here is our control volume. These control volumes don't have to be a perfect representation of what the shape is. Right? We just have to kind of get an idea. So this will be our control volume. We have a control surface at the end here. So that means we know we have A positive outward. In this case, we have the flow going out of the tank. So our velocity is also going to be positive outward. So they're going to be in the same direction. So what can we say? We can say we have a fixed control volume. Right? The volume of the tank doesn't change. Fixed control volume. And we have air, right? So it's going to be spread out throughout the entire container. We have a compressible fluid. And we're actually interested in the change of density within the fluid. So compressible fluid. We already said we have unsteady flow. And for the outflow at the surface, we're going to assume we can use average velocities. All right, with that, I think we have everything we need to get started. Right? So we can go ahead and once again write our continuity equation. d dt, integral over the control volume of rho dv plus integral over the control surfaces rho times v dA, and all that has to be 0. All right, so now in our case, we know that we have internal changes. Right? The volume doesn't change, but the density will change. Right? The density is in here, so we have to leave that in. So, but we have a fixed control volume, so we don't have to do any integration. We can just write directly d dt of rho times the volume plus, and then the flow, if we want that's coming out, right, is going to be just whatever the flow at that specific time is. C current, a rho current times the outflow. Right, so we can also say that the volume is not changing, so we can pull that out. So we can say this will be same as V times d rho dt plus the current density times Q. And all that has to be equal to 0. Right? And of course, the d rho dt is what we're looking for. So we can solve that for d rho dt. That means, not partial, but regular. D rho dt is then minus the current density times the flow rate. So this is basically a mass flow rate divided by the volume. All right, so if we want to find our current density, we have to go to the ideal gas law, right? We know that P is equal to rho current times R times T. That means rho current is P over R times T. All right, so we can take that and plug back into our equation. So that means d rho dt is gonna be minus P over R times T times Q over V. Or if we write this nicer, we get P times Q divided by V times R times T. All right, now P is given to us, Q is given to us. This is not a velocity, this is a volume. Let's erase that, make that clear. That's not what I wanted. Wrong button. So what I wanted to have is P times Q over V times R times T. There we go. Make it a little clearer. So we're given the volume. We can look up what the gas constant is, and of course we're given the temperature. So this would be then minus 480 kilopascals. Flow rate was given to us as 0.05 cubic meters per second. The volume was given to us at 6 meter cubed. R we can look up, that's 286.9. So it's usually given as joule per kilogram per Kelvin, but we'll automatically write that as Newton meters divided by kilogram and Kelvin, because of course we know that we have newtons up here, so we can cancel those out. And then times 30 degrees C. And then if we convert that all to units that are consistent, then we'd have minus 480 times 10 to the 3 Newton per meter squared. Right, that's a Pascal. 0.05 cubic meter per second. We don't have to worry about that one. Same with the 6 meter cubed. 286.9 Newton meter per kilogram Kelvin, and then to convert to Kelvin, we'll just add 273, and that's Kelvin there. All right, and so then we can see we have the Newton cancel out. We have the Kelvin cancel out. We have a kilogram down here, so we flip up. We have square meters and cubic meters, so there's a meter up on top, and we're dividing it by to the fourth, so we'll have kilogram per cubic meter. So we come out exactly what we want. So that'd be 0.046014 kilogram per cubic meter, and we're looking at the rate of change. So we have that second there too, right? So kilogram per second. So our answer is going to be for 3 significant digits, 0.460 kilograms per meter cubed per second. Where did we say that? All right, so that means as time goes by, our density goes down, which fits to what we're looking at, right? If we think about our tank here, right, as air flows out, the density is going to go down because the change of conditions.